Welcome back to another video in our statistics series. So today we're going to be taking a look at statistical distributions, and this is usually chapter 6 in your, if you have any of the textbooks that you follow here in the UK. So this is a chapter which is actually not too difficult if you just follow along. A lot of it at school can seem a little bit confusing, just like the rest of stats as a whole, and that's because there's quite a few definitions you have to learn, but the kinds of questions you do won't be too difficult if you're able to understand the chapter previously on probability. So in this lesson, we'll be taking a look at how to understand what is a discrete probability distribution. We'll try to understand what the binomial distribution actually is. And using the binomial distribution, we'll figure out how to find probabilities from there and how to get cumulative probabilities from there. So this is a relatively short chapter, so there'll be quite a few exercises in this video compared to theory. So hopefully it should be quite easy to follow along. So let's just jump right into it. So let's take a look at what are discrete random variables. Well, to understand what a discrete random variable is, let's break it down into what does discrete mean? What does it mean to be random? And we already know what a variable is. A variable is something which can take any value. So let's just try and understand each of these three parts of what a discrete random variable is, and that should make it a lot easier to understand this word whenever someone says it to you in statistics. So a random variable is a variable whose value will depend on the outcome of a random event. So this random event could be me rolling a dice. So if I roll a dice, the outcome of this random variable depends on what happens when I roll the dice. So if I roll the dice, I could get a 1, 2, 3, 4, 5, or 6. But I don't know what's going to happen until I've done this random event and I've got the random event giving me some sort of outcome. So that's a random variable. It's value, and normally we might call it like x, y, or z, doesn't really matter. But let's say you said x is the value of a dice roll, then this variable would depend on what happens when I roll the dice. So that's what a random variable is. So the sample space is the same thing as what we said before in probability. It's just all of the values that a random variable can take. So before we said the sample space is all possible outcomes. So that's pretty much the same thing here. It's all different possible outcomes. So in the case of a dice again, that would be equal to 1, 2, 3, 4, 5, or 6. That's the sample space for my dice. So then now we have to understand what does it mean to be discrete. So if you're discrete, that means you can only take certain values. So we've already talked about what it means to be discrete and continuous. So this is the same thing. You can only take certain fixed values. So a dice can be like 1 or 2, 3, etc. But it can't be 1.5, 1.6, 1.111, stuff like that. It can only be those fixed values. Then moving on from there, we have to understand what does it mean for you to be random? Well, random means that we don't know the probability until we do the experiment, because if we knew what the outcome would be without doing the experiment, then it's not random anymore. So in order to know the probability, we have to actually do the experiment, and that's what it means to be random. So you don't know until you've done the experiment. And then finally, let's understand what is a probability distribution. A probability distribution just describes the probability of any outcome in the sample space. And what I mean by that is, let's start by this. It says it's the outcome in any sample space. So what is our sample space? A sample space is 1, 2, 3, 4, 5, 6 rolled dice. And a probability distribution will describe the probability of each of these outcomes. So in a fair dice, this should be equal to 1/6 on each. So that's kind of what a probability distribution is. It's telling you what outcomes you have, and it's also going to tell you what is the probability of each of those outcomes. So that's the idea of a probability distribution. So hopefully if you put all of those separate words together, you can understand what we mean by a discrete random variable, otherwise known as a DRV, in case I just can't bother to write that out anymore. So yeah, that's pretty much that. So let's actually move on to seeing how we can do some questions on this. So let's say one of the questions, actually, oh yeah, I realized before that I should probably also show you how can you actually show a probability distribution. So there are actually three ways that you can show a probability distribution. One is through the probability mass function, which we'll take a look at. One is in tabular form, and one is as a diagram. So we'll go through each of the different ways you can express a probability distribution. So the probability mass function is just trying to say that the probability that my discrete random variable x takes on a value x, which I have to choose, is 1/4. And this is for values of 1, 2, 3, and 4. So this means the probability that x equals 1 is equal to 1/4. The probability that x equals 2 is equal to 1/4. the probability x equals to 3 is a quarter, and you can see the pattern and so on for the last one. So this is saying, in order to find the probability for x, I can put in any of these numbers into here, and that number will have this probability. Now here it's fixed as a quarter. If you imagine the probability was x is equal to, let's say, 2 lots of x divided by 10, I'm just making that up on the spot, then if I put in, like, for example, 1, then the probability that x is going to equal to 1 is going to be equal to 2 times 1 over 10, which is equal to 2 over 10, which is 0.2. So that's how you can use probability mass functions to find probability. So you basically input these numbers in there to find it. And if there's an x here, then you replace that x over here as well. But we'll look at some questions and how to do it. And just note that if you sum up all these probabilities, all the probabilities should add up to 1, since the rule is that probabilities always add up to 1. So apart from that, we can also express it as a table. So here you can see we've said the value of x can be 1, 2, 3, or 4. And these values go in here again. And the probability of, for example, x being 1 is equal to a quarter, and so on. So this is another way you can write it in a table form. And then the final way is you can do it in a diagram. So in a diagram, we've said the y-axis is a probability x equals x. This is probably this is a chance of, or this is just x itself. And then the probability of x being 1 is a quarter, x being 2 is a quarter, 3 is a quarter, and 4 is a quarter. Sometimes you might have different probability distributions, which might look something like this for different things. So that's one you might have seen quite often because it's something like that. In this case, it's just straight because it's just a straight line. So when we have all of these probabilities, if the probabilities are all the same, like in this case, the probabilities are all 1/4 each, then we call this a discrete uniform distribution. And the fact that shows you it's straight is the word uniform. Uniform means that everything is the same. So yeah, those are the 3 different ways in which you can express the different probabilities and the distributions. So hopefully you're comfortable with that. And we'll take a look at some questions on how you do that. Okay. So now let's try to do an example question on how to use these probability distributions. So we'll go through 3 different examples of how to use these, and hopefully that will get you familiar with what we've just learned. So let's say we toss 3 fair coins, and we want to figure out what are the possible outcomes we can get. And then we want to draw the probability distribution as a table and as a PMF. So we'll show you both ways to do it. So first of all, if I'm tossing 3 coins, what are all the possible outcomes? Well, I could either get 3 heads. That's one of the possible outcomes. I could either get heads, and tails. I could get heads, tails. I could get tails, heads, or I could get tails, heads, tails. Then apart from that, I could get tails, head, and finally I could get all 3 tails over there. So as you can see in my probability distribution, there should be 1, 2, 3, 4, 5, 6, 7. And there should usually be 8. So I'm probably missing 1 out in here. So that would probably be this one here, which is heads, tails, heads. So because there's usually 8 for this kind of question. So yeah, you can see all these are different, and these are your different possible combinations you can have. So this is the answer to all the possible outcomes you could have. So there's 9 possible outcomes in total. Okay. So now the next part of the question says, can you show this as a probability distribution, one as a table and one as a PMF? So if we're doing it as a table, it's quite simple. We'll say the number of heads, like that, and we'll call that x. And beneath it, you can always just write probability of x equals x. That's always the same. And as a table, let's put in, there's only going to be 4 columns, and the reason is I can either get 0 heads, 1 head, 2 head, or 3 heads. So since I know already that there are 8 possible, oh my bad, I wrote 9 before. That should have been 8. So there's only 8 possible outcomes. So I know all these probabilities are out of 8. So how many of these have 0 heads? Well, the ones which have 0 heads are only this one here, actually, the one that everything is tails. So I have 1 out of 8 for that. How many of these only have 1 head in them? So that would be this one here, and this one here. So that's 3 out of 8. How many have 2 heads in them? Well, that would be this one here, and this one here. So again, that's 3. And which ones have all 3 heads? Well, that's just heads, 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 which is 1. And that's it. That's all you need to do to draw a probability table. Now that you've got the table, actually, we can also represent this as a PMF. So in order to do that, we'll say the probability that x is equal to x is going to equal to, and this is how you normally write it. You draw something like that, and you'll write down all the different probabilities. So you can see that here we have 1/8, and here we have 3/8. So what we'll do is we'll write the common ones we've got down. We've got 1/8, 3/8, and then as convention, you always write 0 here. So which cases of x gave us 1/8? The only ones that gave us 1/8 were 0 and 3. So what we write here is when x is equal to 0 or 3, the probability distribution is telling us that when these are 0 or 3, the probability is 1/8 over here. In which case is it 3/8? Well, that's when x is equal to 1 or 2. And then we write it's 0 otherwise. In this case, none of them are 0. So if we have any number, like let's say someone said, what's the probability that x equals to 7? Well, x equals 7 is none of these or none of these. So it falls into the otherwise category, which tells you the probability is 0. That's why this probability would be equal to 0. But that's pretty much it. That's how you can draw your probability mass function for a question like this. So now let's move on to another example. And let's say I have a biased 5-sided die, and the number I roll is going to be denoted by x. So x is my random variable, which I can only know the value of this variable once I've done my experiment, which is rolling this 5-sided dice. So depending on what happens when I roll this dice, I'll get an answer, which is what I put into x. And I'm given that the probability distribution for this is x equals x is equal to k over x. So I know what my thing is. So first thing is they want me to figure out what is k. So how can I solve a question like this? Well, first of all, before we start, let's draw our table for this question. So for x, the probability that x equals x, then the values that x can take is it's defined for as a 5-sided dice. So there's only 5 things I can roll. I can roll 1, 2, 3, a 4, or a 5. So if I have all of those, then that means that the probability that, for example, that x equals to 1, how would I do that? So I know the probability that x equals x is k over x. The probability that x is equal to 1, all I do is put that 1 into this x here, so I get k over 1. The probability that x is equal to 2 is just k over 2, and so on. So all you can see, all I've done is I've just had to replace the x here with whatever is over here. So I put a 1 there, so I put 1 down there. So it's just k over 1, k over 2, k over 3, k over 4, and k over 5. Now I know based on the rules of probability that all of these will add up to 1. So the probability of k over 1 plus k over 2 plus k over 3 plus k over 4 plus k over 5 should equal to 1. So now all I need to do is solve this equation. And this is a fairly simple equation to solve. So I just take the k out as a factor, and then I have 1 over 1, which just gives me a grand total of 1, plus a half, plus 1/3, plus a quarter, plus a fifth, and that equals to 1. So now I just need to add up all of these, which means I need to find the common denominator, unfortunately. So taking a look at that, I guess we could do 60. So 1 plus, if all of them are over 60, then the answer for this one would be 30, this would be 20, this would be 15, and this would be 12. So now let's add them up. So k is 60 over 60. So I'll just rewrite the 1 as 60 over 60. Plus 30, plus 20, plus 15, plus 12 equals to 1. Therefore, it's quite a long question, but let's just carry on. So 60 plus 30 is 90, 110, 125, 137 over 60. Hopefully I've added that correctly. Equals to 1, therefore k is equal to 1 divided by 60 over 137 over 60. or what I was trying to say is if you divide it by 137 over 60, it's the same as multiplying it by 60 over 137. So it's just 60 over 137. And that is your answer for k. So now we know what the value of k is. That's pretty much how I do it. So it seems like quite a long kind of question in terms of how you do it. But that's pretty much it. So now the next question says, can you write the PD as a table? Well, we know what k is now. We know that k is just equal to 60 over 137. So all we need to do actually is, if I copy this table down for part B, and we put that down over here, then all I need to do is, for these questions, is just replace my k with the value of k I actually got. So k divided by 1 would simply give us 60 over 137. Then k divided by 2, we have to divide that one by 2. So we'll have to go through that. I'll just pause the video here and I'll actually calculate it because I realize it's quite a long one. So I'll just do all the calculations and skip ahead. Okay, so back to the video, you can see we've just calculated the numbers and put them in. Now the key thing was actually wasn't that difficult. I had written a different number here before, but that was before when I didn't bother to cancel out the numbers we had at the bottom. But if you cancel them out, you can actually cut it and get a number like this. But basically, if you do the calculations, these are the numbers that you'll get, and this will be the probability table that you need to do. So now in the questions, it asked us what is the probability that x equals 2, or x is more than 3, is between 2 and 5, and it's more than 5. So if we have that, if we just put that down here, and let's actually try and solve each of these probabilities, then based on that, what we can see, the probability that x is more than 3, which values would that one be? Well, that one would be more than 3 means you have to be, can't be 1, can't be 2, can't be 3. You have to be either 4 or 5. So the probability that x is more than 3 would be the probability of x is 4 plus the probability that x is 5, which adds up to 27 over 137. And how did I get that? I just added up these two because that's from these two probabilities. Then what's the probability that x is more than 2? So it's everything here, but it's less than 5, so it's everything this way. So more than 2, less than 5 means basically only 3 and 4, since that's more than 2 and less than 5. So again, we add up those probabilities, 20 over 137 plus 15 over 137, and you get 35 over 137. And finally, what's the probability that x is more than 5? Well, unfortunately, there's nothing else after 5. So the probability of x being more than 5 is just going to simply be 0. And that's it. That's how you solve this kind of question. So you can't get these kind of questions where they ask, solve k. And to do that, you need to put all your values of x into your graph first. So you get this table, then make them all equal to 1. Add up that, make that equal to 1, and then solve it for k. That's it. Once you have k, you can put it back in, get your table, and then these questions are quite simple. So that's how you do that second kind of example. Now let's take a look at a third and final example. So if you have a spinner and you spin it, we have a spinner here which basically has 3 green portions to it, and the rest of them are all red. So as you can see, there are how many portions are? Let's count them. 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 portions, of which, let's draw them black. 8 portions, of which 3 are green, and 5 of them appear to be red. So based on that, the question says you spin the spinner until you either hit the green part or you span it 5 times. So if I span it 5 times and I haven't hit a green one yet, then I stop. So what's the probability distribution of how many times you spin x? So to do this, we need to figure out. So x is the number of times we'll spin it. The probability of x being x, basically we just need to fill out this probability distribution. So we can only really ever spin it either once, because we either land in the green straight away, or we spin it twice, 3 times, 4 times, still haven't landed in green, and 5 times. So 5 is the maximum time because after 5 we stop. So how can we find each of these probabilities? Well, to do that, we need to say what is the probability that we will land or stop the first time. The only way we can stop the first time is if we land on a green straight away. So let's say we landed on a green straight away. The chances of that happening out of 8 things, only 3 are green. So that will quite simply just be 3 over 8. So now so this is simply coming from, if I make a note, from 1 green. Now what is the probability of us landing and stopping after 2 attempts? So that's if we had a red first, and then, so we have 1 red, and then that is followed by a green, meaning that we stopped. So the chance of 1 red followed by a green, well, a red has a 5 over 8 chance, times that by the chance of green, which has a 3 over 8 chance. So then we have a 15 over 64 chance of getting a number like that. So that's what we do for this one over here. Next, what's the chance of getting 3? Well, for 3, what happens is you have to have 2 reds followed by 1 green. So to do that, we have to get 1 red times another red times 1 green, which will give us that. So 5 times 5 will give us 25 times 3 gives us 75. So 75 over whatever 8 times 8 times 8 is. I'm just going to write it like that. Then same one for this. How can we have it 4 times? Well, that's 3 reds and 1 green. So that would be 5 times over 8 times 5 over 8 times 5 over 8 times 3 over 8. So that would be 125 times 3, which will give us 375 over 8 to the 4. So just for consistency, if it's easy, I can write this one as well as 8 squared instead of 64. And then finally, how can we have this as being 5? Well, that means if all 5 are going to be reds. So how can we get 5 reds? Well, that's if I have 5 over 8 and I do that 5 times. So what's that going to be equal to? That's 5 times 5 times 5 is 125 times 5 is 375 times that by 5. So let's just put that into our calculator. Lost track now. So that's 3,125 over whatever 8 to the power 5 is. But that's your numbers, and that's how you answer a question like that. And that's it. And then you've basically found how you've done it. So the key thing here was you have to ask yourself, okay, it says, what's the probability distribution of how many times you spin X? So first you ask ourselves, what are the possible outcomes? Well, we can only spin 1, 2, 3, 4, or 5 times. And then we ask ourselves, how can we get only 1 spin? Well, that's if you have 1 green. How can you have 2 spins? That's if you have 1 red and 1 green. How could you have 4 spins? That's if you have 3 reds and 1 green. And that's pretty much what you have to do. And that's how you answer this kind of question. So I hope that was helpful. So next we're going to take a look at the binomial distribution. So this is one of the new distributions that you're going to learn and you're going to be using quite a lot. So the binomial distribution is used only when you have an experiment which only has 2 outcomes. So if you do something which only 2 possible things can happen, then you can use a binomial distribution. And normally we call one of the things that happens a success and the other one happening is like a failure. So one of your outcomes is success, the other outcome is a failure. But the key thing to remember is you can only do it when there's 2 outcomes. So our random variable x in this case will represent the successful number of trials. So whatever x is talking about is always going to be saying how many successes we had. So if I wanted to find out if I flipped a coin, the chance of getting heads and tails, then a success might be heads and a failure might be tails. So x would tell me how many heads I have since that's a success. And the trials have to be independent of each other. In a binomial distribution, if the trials will affect each other, then that's not a fair test. And then you can't use the binomial distributions. So every time you roll a dice or well, let's say you can't use the dice because there's 6 sides and we said it's only 2 outcomes. So let's say you flipped a coin, there's only 2 outcomes, but every time you flip the coin, it shouldn't affect another coin flip, for example. And that's just, these are just rules that they might ask you to remember in the exam. So just remember that these are your rules. So let's take a look at the binomial distribution itself. And like everything in stats, at the beginning, this might seem off-putting, but we'll go through it and how to use it. And hopefully that will make it seem much better than what this actually seems to look like. So the first thing to understand is when you have the binomial distribution, we say that x is distributed binomially. So doing this means that a random variable x is distributed binomially. This tells us what the distribution is. So you can see here it's a binomial distribution. And we say for the binomial distribution, we need to know 2 things. How many trials we did, so how many times we ran the experiment. So this would be how many times did I flip the coin? And what is the probability of a success? So let's say my coin is biased. The chance of a heads, it's like 0.6. So then, and I flipped it 100 times, then I would say X is binomially distributed for 100 flips with the probability of success of a heads of 0.6. So that's what I'd write for my binomial distribution. And then after that, you probably want to find the probability. So if I did it 100 times, what's the probability that my coin would give me a total number of, like, let's say 72 heads in 100 trials? To do that, what we need to do is use this equation here. Now, this one will look really off-putting, but let's actually talk about what this equation is. So P is a probability of success. 1 minus P is just a probability of failure. R over here is the number that we're looking for. So R would be how many heads we had. So let's say we wanted to find the probability that we rolled 72 heads. So following this formula, this part here is just n choose r, which you've probably studied before. This is a choose function, which you have in calculator. So n in our case is we had 100 trials, and we want to know how many heads was there, how many times we got 72 heads, basically. So what's probably 72 heads? So we write 72 here. The probability of a success was 0.6. Then you raise that to the power of how many heads you wanted. And then the next part looks complicated, but it's simply going to be 1 minus p is 0.4. So this is the probability of a failure. And n minus r is just 100 minus 72, which is 28. So the way I like to think of this part over here, which just went away, is basically, I like to think of this as being the probability of a success times how many successes I have. And this is the probability of a failure, and just times how many of those happen. So if I had 72 successes, I had to have 22 failures, and the chance of success is 0.6, and so there should be 0.4. So that's all you have to do these kinds of questions. So I'll show you some examples of how to answer this. So let's say X is binomially distributed 20 and 1/5. So in order to do that, for probability of X being 3, all we need to do is follow the formula. So what I'll do is I'll copy this formula down, just so we always have it there. And let's actually try and use it. So that's our formula. So the probability that X is equal to 3 should be equal to, well, I've had 20 trials, that's my n. 3 of them are successes. The probability of success here is 1/5. So it's 1/5, like we said. And therefore, what is the probability of failure? If you want to write it in this way, you can do this. Before the powers, let's say probability of success is 1/5. Probability of failure is 4/5. And how many successes do I have? 3. And how many failures would I therefore have? Well, in 20 trials, if only 3 are successes, then I can only have 17 failures. So the answer would quite simply just be this. That's it. And whatever you get when you put that in your calculator would be the answer. Just in case you're stuck, this is known as the choose function, the NCR function on your calculator, which you should have. So the 20 is the n, the r is the 3. So you can just write that in, even in case you were stuck with that. Then we've also got the probability X is 10. This is the same thing. So again, we have 20 trials still, but now 10 of them are successes. So the probability of success and failure remains the same, but the only thing that changes, 10 of them are successes, therefore 10 of them are failures, and it's as easy as that. That's what you need to do. The next one is also just as easy, but you just need to break it down a bit. So the probability that X is less than or equal to 2 is the probability that X is either 0 plus the probability that X is 1 plus the probability that X is equal to 2. That's it. And if you just put all of those into your calculator, you will get your answer. Obviously, you have to write the binomial version of each. So the probability of 20, choose 0. The probability of success is 1/5, 1/4. So 0 for here, 20 for here. What you actually notice is this whole thing here. 20 choose 0 is just 1. 1/5 to the power 0 is just 1. So this ends up just becoming 4/5 to the power 20, actually. Then this one here would be 20 to the 1. Again, 1/5 and 4/5. 1 success, 19 failures, whatever that is. You add that up. And then 20 choose 2, 1/5, 4/5, 2 and 18. And that's it. That's how you answer that kind of question there. So let's take a look at another question now. So here we've got the probability that someone in the class likes the color blue is 0.25. And instead of asking everyone in the class, we take a sample of 15 students. So what's a good model for the number of people who like blue, which is X? So this one's actually quite easy. This is quite simply the binomial distribution for X, which is the number of people who like blue, is binomially distributed between 15 students, and the chance that each like blue is 0.25. And that's quite simply all you need to do for this question. And that will be the answer to the first part. And the reason you say this is correct is because, let's say the probability that they like blue And actually, to make the question right, I should say they either like blue or don't like blue. Is that because if you can like more than blue, you feel like the many other different colors, then there's only two outcomes, so it's not binomial. But the probability that I say you either like blue or you don't like blue, so it has to be one of the two, then this question will make sense. There's only two outcomes: either you're blue or you don't like blue. So they'll ask you like, why can I, why is this a good model? Well, the first thing we said is there's only two outcomes, so either you can be blue or you don't like blue. And there's a fixed number of trials. There's 15 trials, so that's already fixed. And we have a fixed probability of success of all the trials. So that's a probability of each of them liking blue or not. So all of that is basically fixed. So assuming all the samples are independent, so every time you ask a student, it doesn't affect it because that's the last condition, then we can say that you're allowed to do it. So that's why I said, remember those rules we said before, because when they ask you why is this a good model, then you just state those rules and you fit in all the things for the model. But basically you can get this as a result. Now we need to find the probability that exactly 6 people like blue. This one's quite simple. The probability that x is equal to 6 would just be equal to, again, we have 15 people, 6 are successes, so 6 are like blue, so then 0.25 is a success, therefore 0.75 is not a success. 6 people like blue, therefore the other 9 cannot like it. 15 minus 6 would give us 9 there, and that's literally all you have to do to find exactly 6. So when it's exactly a certain number of people, it's quite easy. So the next question is asking fewer than 3 people like blue. So what is that saying? That's saying the probability that x is less than 3. Now the probability that x is less than 3 is equal to the probability that x is 0 plus the probability that x is 1 plus the probability that x is 2, but not the probability that x is 3 because it has to be less than 3. So again, if you do the same thing as we did before, this would be 15, 0, probability of success, 0, probability of failure, 15, that to the 15. Again, this just becomes 0.75 to the 15 plus 15 to the 0, 0.25 to the 1, 0.75 to the 14 plus, oops, sorry, my bad. That should have been 15 to the 1. You can just, it's quite common to make silly mistakes in these, so be really careful with stuff like this because it seems like it's quite quick and sometimes there will be a mistake. So 15 to 0.25, this should be a 2, 0.75, this should be 13. You just add that up and whatever you get. And that's pretty much it. That's how you answer questions about the binomial when it's this kind of thing. Now, there's one thing you might have noticed. This is great fun and all if you have to do like probability x is less than 3 is equal to this plus this plus this. But even writing that took quite a lot of time to do all of that. If I told you what's the probability that x is less than or equal to like 10, then I'm not going to expect you to have to write out the probability that x is equal to 0 plus the probability x is equal to 1 and so on. That takes way too long. There's going to be 9, 10 different things you have to write here. That's way too many. So that's not really a practical solution. So this works for small numbers, but what if I have a huge number? We'll take a look at how to deal with that in the next part. So to understand this last part, we just need to understand what are cumulative probabilities. And cumulative probabilities for a random variable x would tell us the sum of all the probabilities up to and including the value of x, where x is equal to or is less than or equal to 10. So if you're doing an example, if you want to find out the probability that x is less than or equal to 2, then that's all these 3 probabilities added up. And we'd actually have a table which would directly tell us what this answer actually is. So you don't actually need to do this. You can actually put it into a calculator. There is a cumulative button in your calculator which basically helps you find cumulative probabilities. So you should find out how to use that because that's usually the way you do it. Or if you go to the back of your book, you'll probably find some sort of binomial table, and that table will show you how to read the binomial tables which you've got. So basically all you need to do is once you've gone to the back, you need to find the table which corresponds to your value of n and the value of p that you want to want, and literally it'll be something like, if this is a table for n equals 10, you might have like 0, 1, 2, 3 all the way down, and then you have the probabilities like 0.1, 0.2, 0.3, and then let's say your binomial thing was distributed as 10, 0.2, and you want the probability that x is less than or equal to 2 as your question, then what you would do for that is you'd find the table for n is equal to 10, you'd find where you have 0.2, and you literally read 0.2 is this column here, so that's the one I want, and I want less than or equal to 2, which would be across here. So this is the value which I would want in my table. So you can just get used to reading that from the table and doing it. So, but to be honest, you have your calculators in these exams, so you could just put it into a calculator and read it off there, which is easier. So the next ones, I would assume you have a calculator, and what would be worth trying is, if you do have a calculator, I would just try these questions. I've written some for you to try out and see what you get for your answers. And I'll post the answers down later in the description just so you can double check your answers with it. But these are just for you to check. So the only thing, there's nothing really new here, which is why we don't need to go too much. But basically, to do this first question, for example, you would put n is equal to 10 into your thing. Again, you'd find where it's 0.3 for your probability. This would be 0, 1, 2, 3, 4, 5, 6. It would be easier if I drew till 6 since it goes till 6. But for this question, you use this column, this row, this number would give you the probability that x is less than or equal to 6. So you'll just get a straight number for that. Now, these other questions, you just want to be a bit careful, because probability, this table that you have, right, only gives you the probability that probability of x is less than or equal to x. So if you were to do this question here, this doesn't, if you just searched up 5 in the table and matched it up, that wouldn't work, because you notice this is missing. So you have to always convert these questions into the form or something like that. So if you convert this question to the form, what you actually need to search in your tables is a probability that x is less than or equal to 4, because these two are the same. Since the probability of every x being less than 5 is the probability of x being less than or equal to 4. And that's just something you'll need to get used to in cumulative probabilities and trying to understand that. And the final question we've got is, what's the probability that x is more than or equal to 15? I realize that question doesn't actually work there, so let's change that. Let's just make that 3. The probability x is more than or equal to 3. Well, how do we do a question like that? So you can see that here we've got the inequality sign flipped around. Well, if you're doing a question like this, quite simply, all you need to do is you can rewrite this as the probability, or as 1 minus the probability that x is going to be equal to less than or equal to 2. And why can I do that? Well, the probability that x is more than or equal to 3 is equal to the probability that x is either equal to 3 plus the probability that x is equal to 4 plus the probability that x is equal to 5, and so on, all the way to 10. So everything which is not included, which I'll put in red, is probability that x is equal to 0 is not included, x is equal to 1 is not included, and x is equal to 2 is not included. So these things, if you put together, that's the same as saying the probability is x is less than or equal to 2. So that's how you rewrite these. So whenever you get a question and you're looking at the tables, if it's not in this form, if you have something which is less than, this is how you would convert it. If you have something which is more than or equal to, then this is how you convert it. And just get used to converting things where it's like more than, less than. So different types you have to be careful are, which is less than equal to, which is fine because that's what your table tells you, or more than or equal to. Just need to be careful with that one as well. So that's pretty easy to understand. And a good thing I would say is, if just for a bit of help, if I got rid of this equal sign, then this will actually change my answer, because this says the probability of everything which is more than 3, which means that I can't include 3 in itself. So where I had 3 here, I can't include 3 anymore, because 3 is not more than 3. And actually that goes in the bad section here. So actually, if I was doing that question where it's more than without the equal sign, this would change and be x is less than or equal to 3. So just kind of play around with that, do some questions on it and get used to it. But this should hopefully help you understand that part over there. So we can finally take a look at a last question, and this is probably the hardest kind of question which you can expect. So when you do this kind of question, we said we have a dice and there's a chance that it will land on a 6, and the chance it lands on 6 is 0.2, and we roll it 15 times. So what's the probability that we have no more than 3 6s and at least 7 6s? So these are like the word kind of problems that people don't tend to like. So this kind of question is, we know x is binomially distributed with 15 rolls and the chance of success is 0.2. So the probability that x is no more than 3 times, now that's the key part, it says no more than 3 times. That means that I have to be less than or equal to 3, because I can't do that more than at least 3 times. So you just have to find that probability. And like we said, you know how to find that in a binomial table or using your calculator. And that's it. You just put in 15, 0.2 in your calculator for the cumulative binomial and you get that. For those of you who don't know how to do it, I'll make a video on just how to use a calculator to do that. But I think most of the people watching this video probably already know that. So then finally, part B. At least 7 sixes means that the probability of x has to be at least 7, which means it has to be more than or equal to 7. That's what at least means. So again, to do this, we have to do 1 minus the probability that x is going to be equal to less than or equal to 6. So that's using what we said before. You can find this in your calculator or the tables again, and again, you'll get your answer straight away. So that's what you need to do for this kind of question. Now, the last part is the hardest part you can expect in the whole chapter in a question like this. So if we use the dice to win a raffle, then let's say I said, okay, now I know my dice has a 0.26% chance of getting a 6. So I say that, okay, I want to make a competition that people roll the dice to win a raffle, and we want the chance of them winning to be less than 0.05%. And because everyone can roll 15 times, how many 6s should I set them to roll so that the chance of winning a prize is less than 0.05? Because if I said, like, you know, in 15 rolls, you just have to roll 1 6, then you will win a prize, and the chances that you'll win the prize is quite high. So I don't want to do that. I want to limit it so I can make some money in the raffle. So in order to do a question like that, what we have to say is we say, let's say y equal to the smallest number of 6s needed to win a prize. So we say that y is the smallest number of 6s you need to win a prize. So, you know, if you needed 10, there's no point. We'll say what's the smallest number you need to win a prize. So what we're trying to say is we want the probability that x is going to be more than or equal to this random thing that we called here as y to be less than 0.05. So we want the chances of, so let's just what was x again. X is the number of 6s and y is the smallest number of 6s we need to win a prize. So we want our random variable x to be more than this value of y that we have. So what we need to do quite simply is figure out what value does this y have to be so that this is 0.05. Now again, from our tables, we can't do this so easily. And why is that? Well, that's because we have a more than sign. So remember, you have to do 1 minus the probability that x is less than or equal to y is minus 1 should be less than 0.95. So then basically just look in your tables, find a value of the first value, which when you do 1 minus, that will give you something which is less than this value here. And whatever you get for that will be the smallest number you need to roll. So I'll leave this for you as an exercise to do. And then once I put up the videos on how to actually answer these kind of questions, I'll put like a fully worked solution, but it'll be a good idea to actually challenge yourself on this kind of question to see how you do it and to stretch your understanding on how to do this. So yeah, I hope the video was helpful overall. And there's one more video to go in the series, which will be the 3rd chapter on box plots and all of that stuff on representing data. So that should be quite a simple topic. So I've left that to the end. And as ever, if this was helpful to you, then please let me know in the comments below and I can continue making these videos for this subject and all the other ones too. So I'll see you in our next video.